MPC854XE PowerQUICC processors by Freescale Semiconductor. Welcome to the training module on the MPC854X device. This training module introduces the features of the E500 core and supporting devices, its peripheral functions incorporated into this device. Key features include a 256 KB L2 cache, integrated security, 64-bit DDR 1 and 2 scaling up to 400 MHz data rate, 32-bit PCI, 4-bit serial rapid I/O or 4-bit PCI Express, and 2 GB Ethernet interfaces. With clock frequencies scaling from 800 MHz to 1 GHz, this cost-effective device is ideally suited for a wide range of general-purpose embedded control applications such as robotics, discrete manufacturing, and process manufacturing control. The processors are designed to offer clock speed scaling up to 1.333 GHz with headroom for 1.5 GHz. They combine the powerful processor core, enhanced peripherals, and high-speed interconnect technology to balance processor performance with I/O systems throughput. Processors offer a wide range of high-speed connectivity options, include gigabit Ethernet, serial rapid I/O technology, and PCI Express. Support for these high-speed interfaces enables scalable connectivity to network processors and/or ASICs in the data plane where the PowerQUICC handles complex, computationally demanding control plane processing tasks. These processors also feature next-generation double data rate or DDR2 memory controller, enhanced gigabit Ethernet support, double precision floating point, and integrated security engines that support the Kasumi algorithm needed for 3G wireless security. Here is a block diagram of the processor core complex that shows how the functional units operate independently and in parallel. The E500 processor core is a low-power implementation of the family of reduced instruction set computing or RISC-embedded processors that implement the Book E definition of the PowerPC architecture. The E500 is a 32-bit implementation of the Book E architecture using the lower words in the 64-bit general-purpose registers. The MPC8548E contains an internal 512K-bit memory array that can be configured as memory-mapped SRAM or as a look-aside L2 cache. The array can also be divided into two arrays, one of which may be used as cache and the other as SRAM. The memory controller for this array connects to the core complex bus and communicates via 122-bit read and write buses to the E500 core and the MPC8548E system logic. Memory controller signals are grouped as memory interface signals, clock signals, and debug signals. Signals are organized into the following sections: overview of signals and cross-references for signals that serve multiple functions, including two lists, one by functional block and one alphabetically, list of reset configuration signals, and finally, list of output signal states at reset. The MPC8548E takes a single input clock, system clock, as its primary clock source for the E500 core and all the devices and interfaces that operate synchronously with the core. The system clock input is multiplied by using a phase lock loop to create the core complex bus clock. The CCB clock is used by virtually all the synchronous system logic, including the L2 cache and the other internal blocks such as DMA and interrupt controller. The CCB clock also feeds the PLL in the E500 core and the PLL that creates clocks for the local bus memory controller. The E500 core complex supports demand-paged virtual memory as well as other memory management schemes that depend on precise control of effective-to-physical address translation and flexible memory protection as defined by the architecture. The mapping mechanism consists of software-managed TLBs that support variable size pages with page properties and permissions. The integrated 512K-byte L2 cache is organized as 2048 8-way sets of 32-byte cache lines based on 36-bit physical addresses. The SRAM can be configured with memory-mapped registers as externally accessible memory-mapped SRAM in addition to or instead of cache. The fully programmable DDR SDRAM controller supports most JEDEC standard by 8, by 16, or by 32 DDR and DDR2 memories available. In addition, unbuffered and registered DIMMs are supported. Mixing different memory types or unbuffered and registered DIMMs in the same system is not supported. Built-in error checking and correction ensures very low bit error rates for reliable high-frequency operation. Dynamic power management and auto pre-charge modes simplify memory systems design. A large set of special features, including ECC error injection, support rapid system debug. The PIC prioritizes and manages interrupts directed to the INT signal. It also manages the interrupts generated by the PIC itself and by off-chip interrupt sources. The PIC is compliant with the Open PIC architecture. The interrupt controller provides interrupt management and is responsible for receiving hardware-generated interrupts from different sources, prioritizing them, and delivering them to the CPU for servicing. The PIC receives interrupt signals from 3 sources: external to the integrated device, internal to the integrated device, and intrinsic to the PIC itself. The 2-wire I2C bus minimizes interconnections between devices. The synchronous multiple master I2C bus allows the connection of additional devices to the bus for expansion and system development. The bus includes collision detection and arbitration that prevents data corruption if 2 or more master attempts to control the bus simultaneously. The DUART consists of 2 universal asynchronous receive and transmit. The UARTs act independently. All reference to UART refer to one of these receiver transmitters. Each UART is clocked by core complex bus clock. The DUART programming model is compatible with the PIC 16552D. The UART interface is point-to-point, meaning that only 2 UART devices are attached to the connecting signals. The PCI Express controller provides the mechanism to communicate with PCI Express devices. The PCI Express controller connects the internal platform to a 2.5 GHz serial interface. MPC8548E offers up to X8 interface links. As both an initiator and a target device, the PCI Express interface is capable of high bandwidth data transfer and is designed to support next-generation I/O devices. Upon coming out of reset, the PCI Express interface performs link with negotiations and exchanges flow control credits with its link partners. Once link auto negotiation is successful, the controller is in operation. A block diagram of the integrated security engine's internal architecture is shown. The SEC is a modular and scalable security core optimized to process all the algorithms associated with IPsec, IKE, WTLS or WAP, SSL or TLS, and 3GPP. It is not a protocol processor. The SEC is designed to perform multi-algorithm operations in a single pass of the data. The bus interface module is designed to transfer 64-bit words between the internal bus and any register inside the SEC. The MPC8548E serial rapid I/O controller consists of rapid I/O endpoint and rapid I/O messaging unit. The serial rapid I/O interface provides a rapid I/O port and message unit to communicate with other rapid I/O devices. Rapid I/O endpoints supports 9 outbound ATMU windows, with each window having up to 32 sub-windows except the default window, 5 inbound ATMU windows, logical output packet time to live counter to prevent local processor from hanging when the rapid I/O interface fails. The PCI-X Bus Controller acts as a bridge between the PCI-X Bus interface and the Ocean switch fabric. The PCI-X Bus Controller connects the Ocean to the PCI bus, to which I/O components are connected. The PCI bus uses a 32 or 64-bit multiplexed address data bus, plus various control and error signals. The PCI-X Bus interface supports address and data parity with error checking and reporting. The integrated processor's PCI-X Bus interface functions both as a master and a target device. The DMA controller has 4 high-speed DMA channels. Both the E500 core and external devices can initiate DMA transfers. All channels are capable of complex data movement and advanced transaction chaining. Operations such as descriptor, fetches, and block transfers are initiated by each channel. A channel is selected by the arbitration logic, and information is passed to the source and destination control blocks for processing. The source and destination blocks generate read and write requests to the address chaining engine, which manages the DMA master port address interface. The enhanced 3-speed Ethernet controllers of the device interface to 10 megabits per second, 100 megabits per second, and 1 gigabits per second Ethernet or I2C 802.3 networks and devices featuring generic 8 to 16-bit FIFO ports. For Ethernet, an external PHY or SerDes device is required to complete the interface to the media. Each ET-SEC supports multiple standard media independent interfaces, of which the FIFO interface bypasses the Ethernet MAC. 4 ET-SECs are available, providing flexible options for connectivity and control access at different speeds. The MPC8548E is a very flexible device and can be configured to meet many system application needs. In order to build a system, many factors should be considered. The MPC8548E can be used for control processing in applications such as routers, switches, Internet access devices, firewall and other packet filtering processors, network attached storage, storage area networks, imaging, and general-purpose embedded computing. Illustrated is the MPC8548E in a virtual private network access router that is enabled through PCI Express and Ethernet. It shows the MPC8548E in a redundant array of independent disks controller applications.